to show you what we do with the smart heat meter data and how we utilize that, and then we compare it to the design guidelines in Denmark. So just some background, because maybe district heating is not common for everyone, but it's a city piping network in the ground that supply heat for the buildings. That could be single family houses, it could be hotels like we are now, or multi-family houses. In the Europe, district heating supplies 12% of the total heating demand, and in Denmark we have a lot of focus on it because it's extending from 55% at the moment to 70% into 2045. So when we want to expand this network, we'll need to look into how are the actual demand compared to theoretical. And we'll look into guidelines from the 1980s. So maybe something has happened since then. I believe so. The Achilles heel of district heating, that is the heat loss in the pipe network. That is the drawback of that. So we want to look into, with high-temporal-resolution data, what are the actual demand for the hydraulics and for the heat demand. Because it matters if the diameter of the pipe is this size or this size compared to the water amount there is, and what the heat loss will be. When we collect this data, it also opens up for a more data-driven design approach. So what we do is that we, each building in Denmark have a smart heat meter, and I think it goes for the European Union, and the standard remote collection. So when we just collect data remotely, that is 1 hour resolution. We have enhanced this remote data collection to a 3-minute timestamp instead. And then we also go into not each building, but selected buildings with a data logger to kind of have on-site data collection that gives us a 2-second timestamp. So we know exactly what is the value, the actual value, and what are the peaks. So if we compare this enhanced remote data collection and the on-site, then with the 3-minute values, we can have, if we look at the daily, the figure you see to the left, the crosses, if you can see the green crosses, they don't catch the peaks. But if we go on monthly, which are on the right-hand figure, you can see when I collect monthly data, then I can actually get the 99.9% of the max peaks that is also captured. So I just need more data. The 3-minute remote value, they are quick and cheap to install. I can do it from a computer, but they have kind of a sensitivities to signal disruptions. On the on-site, we capture all the peaks. It is, however, time-consuming and it's quite expensive to install. I have to go there, say hello, open the door, install this meter, and it takes time. But I get a stable data collection and all the data I need. So maybe you're not familiar with what a kilowatt is of heat load in a building, so I'll just shortly explain for you. If you take a single family house, you see in the bottom there is a stable condition. That is what I call base load for space heating. So between 2 and 5 kilowatt for a single family house. And then we go to shower. We either use a handheld shower, which use around 8 liters per minute, or we use a head shower system, which use around 6 liters. The increase you see in the middle, that is a shower. So that will increase this peak. So if we look into the result of the heat load, and now I'm only focusing on the 2-second data. From our measurement campaign, we have 4 single-family houses with 1 and 2 tenants, built in the 1970s, around that. All of them have heat exchangers, and then they have 1 bathroom with a handheld shower. As you can see on the box plot, the top line, red dashed line, that design peak load for a single-family house. The whiskers of this box plot, the top one, is the 99.9%. So it means that the peaks that are above is almost never occur. So around 25% we might over-dimension these pipes or installation. But we need to look into why are these peaks occurring to actually understand the installations. So if we go on a visual peak analysis for one of the buildings with handheld showers, I take that one day there was a high peak on that month, and it only happens 1 in the month. You can see there are 2 peaks on the same day, but they only occur in 12 seconds and 18 seconds. So that's 30 seconds on a month where I have a peak load that's actually according to design criteria. And it happens only because there's 20-minute shower duration. If we then turn into a head shower system, which use more water when we shower, we have 2 single-family houses in the measurement campaign with a family of 4 from 2007-8. Also with heat exchanger, they have 2 to 3 bathrooms. And then you can see on the figure to the right that, okay, the heat load are quite higher. But again, if we zoom into one of the peaks, it only happened for 50 seconds, that these are happening simultaneously. So these are one of the trends in Denmark, and maybe also in more countries, that we actually see an issue with in district heating. One of the last results are 2 multi-family houses or apartment buildings with the top one is with 12 apartments. No, that's a low one, and 37 apartments from the top one. I put in the design criteria again. The box plot also show with the top whiskers a 99.9 percentile, and again you can see we actually in the winter period optimize oversize the pipe over dimension with 25%. So my key takeaway is that this design guideline oversize the service pipe. So the service pipe is the one pipe going to one building. For traditional single-family houses with handheld shower, and then for multi-family apartment buildings with around 25%. And I only showed the data for heat exchangers because that's the one with the highest peak demand. If we're talking about storage tank, it's another story. We don't see that there is a need for changing the pipe size, because then we have this safety margin that also can include the head shower system. So it's actually seemed to fit quite good. But I want to kind of discuss in the future the design criteria. Do we need to deliver comfort at all needs? So all are happy all the time. That one day or the year for 30 seconds, they are happy also. Or do we need to look into energy efficient system? Maybe we can start to design with 90 percentile or percent or 95% of user acceptance. So maybe user acceptance should be included. Yes, and then I would like also to acknowledge the 2 Danish UDP grants and the IEA project and ETS9 for this work and for